first I create a new project and I go to name and standard, and I just enter the name of the file. And then you can see here that we offer 2 different products in this program. The first one is the foundation pile. It's it's a design of a foundation pile according to a range of standards which we implemented. And the second one is the design of noise protection walls in the slope according to a method by Vogt. This one includes the calculation of a dished pulley in the slope, and it's a separate program and it must be bought. But in this webinar, we just focus on the foundation pile. Then I want to show you the analysis standards. Maybe you have already seen this in the other webinars before, but we'll just have a short, quick view on this one. You can find the Euro code here, UC7, and a selection of national standards, the old German standards, and the British standard, the Austria, and Switzerland. And then we choose the Euro code, and there we can see that there are many settings for the national, like many national settings for the Euro code, like Germany, Austria, France, Great Britain, Italy, and Spain. And there's the opportunity to add any other national settings as well, like when you want to calculate with another national settings, you're welcome to add those here. And then we choose Germany in this case, and then you can see here the predefined values for all the design situations. And those values cannot be changed manually anymore. And then we can continue for the to the settings. For the earth pressure, we need the earth pressure for designing with horizontal loads and bending moments. And here in this case, the gene 4085 is selected standardly because it's like mainly used in Germany, but you can also like choose other standards from Austria, Switzerland, or like old German standard, or like the Euro code. We choose this one, and it's still the same for the EC2 and EC3. Like the dimensioning of concrete and steel, we have some national standards here, and we have the Euro code, and there we have also like national settings and the opportunity to add any other as well. Then we say that's okay. Okay here as well. And like there's no graphic input necessary for the piles. Like as you can see, that's just one pile and like actually just one line. So we do offer 2 different input windows. The first one for the pile over here, and the soil layers in the second input window. We start with the pile informations. We offer different pile types here, like bob pile, continuous flight auger pile, the micro pile, drive-in steel piles, like with different cross sections, and the drive-in concrete pile, also with 2 different cross sections, and a timber pile and the ductile drive-in pile as well. We choose the bob pile here, and we the diameter is okay with 0.6 meters. We just leave this, and the pile length can be determined, or it can be calculated based on load and soil parameters. So if you activate this one here, the pile first disappears because it hasn't been calculated yet. So, but we want to see a pile right now, so yeah, I just deactivate it. The pile can be inclined. The standard is 0 degrees, but we enter here 15 degrees, and you can see that the graphic follows the inclination, and then we can go back to 0 again for our example here. Then you can choose a concrete grade for the concrete design. The Young's modulus over here is adapted automatically to the grade. Yeah, you can choose it here, and it's automatically adapted. Go back to 2025. Then you can choose a steel grade. And if you want to put any more reinforcement data, you have here the box at the bottom where you can like define the diameter of the reinforcement bar or the numbers, and also you can add some more information about the shear in the reinforcement. Then according to this European standard 1536, an inclination of imperfection and eccentricity must be applied. These values are regulated in the standard, and they lead to an additional bending moment and shear force. Which is also regulated in the standard is the permanent head deformation. And this should be less than 0.03 times the pile diameter. And yeah, which is in this case with a diameter of 0.6 meters, it's 0.018 meters, which the head can be deformed. Yeah. We can also add specific information for the pile head and the pile foot, which is over here at this button. And you can see here the fixations for the pile head or the pile foot. You can choose if you use a piping, and you can use a foot widening. We don't use it in this example. And you also can add a grouting for skin and foot. So then we continue to the loading. You can add loading cases. Yeah, you can also delete them. But it's necessary to know that those load cases are separate. So it means they're not combined with each other. Positive load is a pressure load, and a negative load is a tension load. And then the load can be applied in the horizontal and vertical direction, or it can follow the pile direction, like when the pile is inclined, that we have like 15 degrees, then the load will be inclined as well. If you have a tension load, you can activate the verification of you can activate the verification for the activated earth block, which is over here. You must add the maximum block width, and the verification will be run then, and yes. So we apply the load now. The vertical load is a dead load with 500 kilonewton. The horizontal load is a live load with 20 kilonewton, and the moment is a live load with 10 kilonewton meter. And then you can see here at the top of the pile the loads. Yes. Then we can move on to the soil layers. The input is divided due to the loading. So you can see two boxes here. The first one is for the vertical loading, the longitudinal loading. And this is divided by the characteristic values and the end for skin friction and end bearing. And then for the horizontal loading and bending moment, we need the elastic bedding. And this one cannot exceed the maximum passive earth pressure. Like hence we need like the soil friction angle, the wall friction angle cohesion, the unit weight, and the modulus of the automatic modulus for the calculation. So like we need all those informations for the pile or like for the soil. So the first layer is a slightly plastic silt. We choose this from the parameter suggestions. You can choose here, it's all in German here, but it's okay. A slightly plastic silt. You can here see you can see the values here. The friction angle, the wall friction angle is 2/3 of the friction angle, like automatically as a standard, and yeah, the unit weight, the automatic modulus, like everything which you actually need. So we apply this, and then we choose cohesive here. The soil is cohesive to get the corresponding recommendations for the skin friction and the end bearing, which is over here then. But we first add the bottom, the depth of the bottom, which is 2.5 meters. Yeah, we need characteristic values for skin friction and end bearing for the design, and we need values for the end bearing for less settlement, depending on 3 different percentages of the diameter, like 2, 3, and 10. Less settlement results that less end bearing can be activated, and those values are used for the resistance settlement line as well. For cohesive soils, the skin friction and the end bearing are dependent on undrained cohesion, and the values, like you can select the value here, like if you don't have your own values probably from like given in a geotechnical report, you can use the selection here, and you can use the deposited recommendations for the skin friction and the end bearing. And those ones here, according to the German standard, DIN 1054, or like the recommendation on piles, like the EA-Pfähle in German, or like any other standards, can be used as well if you have selected them before. Yes. And here, like the values are shown, and you can see a range here, like for 3 different undrained cohesions, and there's a range with the value as well, like a lower, medium, and the highest value. And we choose, like you also can interpolate between all those values, and you can use interpolation from the program. Then you can enter here the 35. And then you can see here the result. You can choose a lower, a medium, or a higher value. We apply a medium value, and it's like automatically filled out. Then we go on to the end bearing. Then you can see like there are always like 3 values for each range. Like because we need like 3 values for the resistance settlement line. And we do the same here. We choose the interpolation with CU 35 kilopascal, and we choose a medium value as well, and say OK. Then all those values are filled out. The value at 0.1 of the diameter must be is the same as the end bearing the characteristic value. So those both values must be the same. But like if you choose the selection here, this will be automatically the same. We will just must pay attention, like when you fill this out, like with your own values given somewhere, you must take care that those values are the same. Then we can create a second layer. We use the parameter suggestions again, and we choose a loose sand. You can see the values over here again. We apply this, and this is a non-cohesive soil, and the bottom is at 10 meters. And this values are already filled out. Then we can use the selection of the skin friction. And for a non-cohesive soil, the values are dependent on the end bearing QC of a penetration cone. And you can see here the range QC from 7.5 to greater than 25. And here's the range as well with a lower, medium, and higher value. And we use the interpolation again. We say it's 16 here and say OK. And then it's filled out. Then we select the end bearing. It's the same here with 3 values per for each range, for each like value. And then we use the interpolation. It's 16 and say OK, and everything is filled out. Yeah. Then we can go to the analysis, but we want to calculate the required length here. So we use this one. And we want to have a permanent design situation. I forgot this. Then we push the analysis, and we go to the output. And here first you can see the detailed information about the standard and like about the design approach, the pile data, the layer, and load cases, and the partial safety factors. And this plot shows the pile and the soil with the required pile length, which is like barely, it's really hard to read, but it's 2.80 meters. And you can see the load and the load transfer on the right side. And yes, the load transfer shows like how the load is transferred into the soil. And you can see here that it's like decreases, yeah, like very lightly. But you can see that the this part of the load is transferred into the soil via the skin friction, and the load which is left at the bottom is transferred via the end bearing. Then you can see the additional loads due to the imperfection over here. And then you can find the analysis of the external load bearing the in design approach 2. Here's the required pile length with 2.80 meters as shown in the plot as well. And as you can see here, that this comes from a condition that the head deformation must be less than a 1.80 centimeter, which is like this, which you put in here in the pile data. So this requirement must be fulfilled. So if we, if like actually the pile could be shorter than 2.80 meters, but it must be that long to have a less head deformation than the 1.80 centimeter. Then you can see here the analysis for the skin and the friction and the end bearing. The utilization is less than 1. Like as you can see, it could be shorter, but we need the pile length. And for the head deformation, and the verification is fulfilled. And then you can see like a more detailed verification for both soil layers and everything in detail. And also like the detail about the resulting end bearing, which is less than the permitted end bearing here. Then the settlement is spread out from the resistance settlement line. In this case, it's 1.147 centimeter. The settlement line is shown on the next page. And then for the horizontal loading and bending moment, we must check two things. The first one is that the characteristic elastic bedding must be less than the maximum plane passive earth pressure over the complete length of the pile at every point. You will see this better in the section forces later in the plot. And the second one is that the sum of the elastic bedding, which is here, from the top of the pile to the center of rotation, which is at a depth of almost like 2 meters, must be less than the spatial passive earth pressure. And both, this is like the verification here. It's less, the utilization is less than 1. And yes, it's important that it's a design approach. So it means that you must use the partial safety factors in this case here. And this verification is fulfilled as well. Then you can see here the pile head deformations and the resistance settlement line. The first line shows, this one here, shows the resistance of the skin friction, like what kind of, like how much load you can transfer into the soil with the skin friction, which is like 167 kilonewton. And then the second line here is the end bearing line. It has 3 breaking points, like from the soil layers here, like 2, 3, and 10% of the diameter, like the settlement here. And adding both lines together results into the total resistance line here. And like with the applied load of 500 kilonewton, we can read out the settlement then, which is about like 1.1 centimeter. Yeah, you can go up here, meter line, and then you can go left. And yeah, it's 1.1 centimeter. The next one is the analysis of the internal load bearing according to the Eurocode 2, because we have a concrete pile. You have the safety factors, and you have the design section forces. The design section forces are like probably not the greatest value of the bending moment. It's like it's the most unfavorable combination of the normal force and the bending moment together, which gives like the greatest value of reinforcement, like the greatest amount of reinforcement, sorry. But yeah, due to the loading, like it's a less loading, we don't need any reinforcement. But according to the standard here, like the EN 1536, we need a minimum reinforcement, which is like shown here. Yes. And then we can see like the design and the sections, like the bending moment, the normal force, shear force, reinforcement shown over the depth. But it's great. It's way easier to see it in the plots. And with the plots of the bedding and the soil pressure, you can see that the elastic bedding is adapted to the maximum earth pressure. The soil pressure increases here, but it cannot exceed the passive earth pressure, and hence the bedding must be reduced then. It just can also like slightly increase, and then it has a constant, like almost constant value until like the second layer is increasing again, because it has like, it's a different soil. But yeah, it's reduced here at the top, depending on the maximum earth pressure. And yeah, you can see those values here as well, shown over the depth. And yes, this is the output. And then I want to add a few things about micropiles. You can choose this one here, micropile. The micropile is like a very has a very low diameter, and it's just used for vertical load, and the load transfer is just via skin friction, which you can see down here, and bearing is not available. And according to the EA-Pfähle, there's no recommendation, there's no approach for a resistance settlement line for micropiles. So we do use a method by Ischelbeck. It's based on empirical values. And the idea behind is that less load results into less head settlement, which increases the stiffness. So we do need the stiffness modulus for 50, 75, and 100%. Like the 100% is like the kind of like normal modulus. Yeah, and if you're if you are a little bit lost in finding those values, you can use the suggestions here, which gives like suggestions from Ischelbeck, like for 3 different soil types. We just use this one here. And yes, the third thing I want to mention about micropiles is that if you apply a tension load, like minus 300, then you there will be a greater safety factor. According to the approval for Gibi piles with a standard corrosion protection and a planned permanent use for longer than 2 years, the steel tension must be decreased from 500 to 230 Newton per millimeter square, and this results into a high safety. And in this case, you can apply a double corrosion, which is like here, or you can say like it's less than 2 years then. But if you choose this one, you have a double corrosion, you have a lower safety factor, like the kind of like normal safety factor as you have in any other cases, and then you need less required reinforcement than in the other case where you would need, like due to the higher safety factor, you would need also more reinforcement. And the last thing I want to show that we can do a buckling analysis. Yeah, you can activate this, and then you can choose the parameters. Like you can say from with depth the soft soil layer starts and ends, or you can also say that you want to calculate the buckling analysis over the complete pile length. You can choose between both. And then we also must tell the program how much the soil supports the pile. And this we have different approaches here. Like one could be that the soil support PF is from the soil layer data, like given in a geotechnical report. Or the second one is the most common one, that the PF is a factor. In this case, like it's like mainly 10.5 times the undrained cohesion. And the other ones are like approaches according to Punch Hansen or Wandorf.